Hey, folks. Hope y'all had a great weekend. Let's go ahead and get started. Just a couple of reminders here. We have a written homework assignment that is due this Friday, and then our exam is due, well, it's given the following Saturday. If you have a conflict with this Saturday, you need to let me know soon, and I will work out arrangements with you. Um, but otherwise, I expect the exam to be in a similar format to the last exam. I'm working on a practice test. I'll go ahead and get that posted up sometime this week. All right. Um, Third reminder is that there is no class on Wednesday. Um, the Wednesday is our third spring break day of the semester. So take the day off, enjoy yourself. We'll see you again on Friday. All right. So let's look at a couple definitions. An Euler trail is a walk in a graph that uses every edge exactly once. It's okay to repeat vertices. In fact, we probably have to repeat vertices, but we have to hit every edge exactly one time. If it starts and ends at the same vertex, we call it an Euler tour. And a graph that contains an Euler tour, we say is an Eulerian graph. So let me show you a couple of examples here. This graph is Eulerian. What it means is that I can pick a starting vertex, say like right here, and I can walk through every edge. So I'm going to go around through these edges. Then I'm going to go around the circle and go across and through the square. And then cross back up to get back to my starting point. And I've hit every edge exactly one time. So that's an example of an Eulerian graph that I can trace through every single edge without lifting my pen from the paper and get back to my starting point. I hit this vertex twice, and I made a turn when I got through that vertex. I also hit this vertex twice and crossed over it each time, but that's okay. We're allowed to hit vertices twice, but we are not allowed to reuse edges. So one of the things I want to notice about this graph is that except for the starting vertex, every time I come to a vertex and leave it, that takes 2 from the degree. I mean, it takes one edge to come in and then one edge to leave. If I hit a vertex twice, the degree is 4 because I had to come in and leave on one pair of edges and then come in and leave on another pair of edges. And even the starting vertex, I had to leave to begin the journey, and then I had to come in to finish the journey, and so that takes 2 edges. And so we have this theorem that a graph that is connected has to be connected in order for me to get to all of the edges. If it's connected, it contains an Euler tour if and only if every vertex has even degree. And it will contain an Euler trail. Remember, a trail does not have to come back to the starting and ending point. Does not have to return the starting point. If it doesn't return to the starting point, then the starting point might have an odd degree, and the ending point might have an odd degree. And so we have an Euler trail if the number of vertices of odd degree is either 0 or 2. But those are the only cases. Okay. We have not formally proved this theorem, but I think the explanation up here sort of gives you an idea of what's going on. Every time we enter and leave a vertex, that takes 2 edges, and since we have to go through every single edge, every vertex has to be hit twice, except for possibly the one at the beginning and the end. And that's where we get the possibly 2 edge vertices in the second theorem. Hierholzer's algorithm is an algorithm that will compute an early Euler tour or trail in a graph that has one. We're going to start at graphs that have a tour in them, and then we'll show you how you have to modify it if the graph doesn't have a tour but it doesn't have a trail. So this looks like a lot of steps, but I'll go through an example in a moment. So this is the basic form of the algorithm for a connected graph that contains only vertices of even degree. We're going to initialize I to be 0, start at any vertex v0, and follow any sequence of edges that have not been previously used until we get back to v0. Okay? And then we're going to call that circuit R0. So we start at some vertex, we wander around through the graph until we come back to that starting vertex. Okay? We know we have to be able to get back to that starting vertex because the degree was even, and so the edge that we use to leave the vertex has to leave at least one edge free to come back to it. So that's why we have even degree here. Call the resulting circuit R0. If R0 contains every edge, then we found an Euler tour right off the bat. We'll go ahead and stop. Otherwise, we're going to continue on to step 3, in which we increment I by 1, and now we could choose a vertex vi, which touches some of the edges that are in Ri minus 1, in other words, R naught, and some edges that are not in Ri minus 1. So this vertex here has to include some of the edges from the previous circuit and some edges to build a new circuit. And so what we'll do is we'll build a second circuit and call that V1. And then what we will do is merge that circuit with the other one. When I say merge it, let me find my pen again here. What I'm saying is we'll start at V0, go around until we get V1, then we'll follow V1 around, and then we come back and we follow V0. So that now we have a larger circuit that starts and ends at V0 that incorporates the new circuit we found at V1. So when we merge these together, we'll call that now R sub I. This is now our R1. Well, if that contains every edge, then stop. And if not, we just go back to step 3. And so, what we do is we've got this loop here. How do we know that that loop terminates? Why must this algorithm terminate? Well, the reason why the algorithm terminates is that in step 3, we're making sure that there are new edges, that we're choosing a vertex that contains edges that were not in the circuit. And so every time we increment I by 1, we're finding new edges and adding them to the circuit. And so the number of edges that haven't been seen yet decreases. And since we started with a finite graph, if we decrease every single time, we eventually have to reach 0. We can't keep decreasing an infinite amount. And so this algorithm will terminate. So we're good. All right. If the graph contains exactly 2 vertices of odd degree, then we have to change step 1. Instead of creating a circuit, we're going to create a walk or not that will go from the one vertex to the other vertex that doesn't repeat edges. Step 1 gets changed a little bit. All right, are we ready to work through an example of Hierholzer's algorithm? I hope so. Let's take a look at it. Let's show that this graph has an Euler tour. Now, we did this graph a moment ago, but let's work through the algorithm. So what we're going to do is we're going to start by picking a random vertex V0. So I'm going to let V0 be this vertex here. And we just wander around the graph, just picking arbitrary edges until we get back to V0. So let's say we wander down to E, down to B, over to A, up to D, up to G, up to H. So my first circuit goes from H to E to B to A to D to G and then back to H. Well, I check and I see that that is not the entire that's not the entire graph. And so I now have to pick a different vertex. And I have to now pick a vertex that contains some edges that have been used and some edges that have not been used. That is an edge that can bridge the gap between the old circuit and the new circuit. So I could use E or D or B. It doesn't matter which one, but I have to use one of them. And so I'm going to pick B, for example. That's going to be my V1. And I'm going to start using new edges. So if I go along here, I don't have a choice. I have to go up. I have to go over. Since I'm only using edges that haven't been used before, I have to go across. And I have to go around. And now I'm back to B. And so I now have, temporarily, I have this being B, C, F, E, D, B. But then I merge them together. So what I'm going to do is I'm going to take this B and expand it out to all of this. And so now I get, so the merged R1 is HE and then BCFEDB and then ADGH. So let me draw through that. That's HEB. So I'm on the red cycle right now. Then I go through CFEDB. So I then trace around the blue circuit here. And then I go ADGH, and that finishes off the red circuit. And I have used every single edge, and I came back to my starting point. So that's how the algorithm works. Randomly move around until you get back to your starting point. If you have to add more edges, pick a vertex that allows you to merge in later. Go through the some more edges, and then insert this where the B is in the previous circuit here. So, all right. So let's try a more complicated example. Let's try this one. Let's show that it has an Euler tor. So again, we can do this without having to worry about being greedy or being sophisticated. Let's say that on my first attempt, I pick a very small cycle. Let's say I'm going to start at C. Let's say this is my V naught. And I go around and I like right back early. I'm hit my C quickly and I've got just tons and tons of edges left. That wasn't a very productive start, but that's okay. My starting circuit is CADC. Okay. So now I have to pick a vertex that shares some old edges and some new edges. So that could be any of the other vertices. So let's let A be V1. And we travel around from A until we get back to A. So this time we might go B, we might go around the circle, up to F, then back over to A. And so we got R1 is A, B, E, F, A. And we merged that by substituting all of that in just for the letter A. So that gives us C, A, B, E, F, A, C. And I still have edges that I haven't used. So I pick a vertex that allows me to connect old and new. So let's let F be V2. All right. And so we're going to start by going around the loop this time. That takes me over to C. It says I have to use an edge that I haven't used yet. I have to go up to B. I have to go over to G. Now I've got some choices. So if I go to F, that's going to go ahead and close off the circuit. But I could also go down to A, over to E, over to D, around this loop, and then down to F. So what does that give me? For R2, that gives me F to C to B, over to G, down to A, to E, to D, and then around back to G, and then over to F. I'm going to substitute all of this in for the F. And so we get, as a completely merged circuit here, A, B, C, A, B, E, then F, C, B, G, A, E, D, G, F, and then finally A, C. And that goes through every single edge, starts at C and ends at C. Except that I have copied this down wrong. This was a DC at the end, so this should be DC at the end, and this should be DC at the end. Let me correct that. All right. And so now we have an Euler core. So that's how the algorithm works. We find a circuit. If it doesn't include everything, we find a circuit that joins onto the previous circuit and then merge them together and repeat until we eventually run out of edges. All right. So that's what it means for a graph to be Eulerian, that we can create a tour through the graph that hits every single edge one time. The related concept would be, what if we visit every vertex exactly one time? Now, we do not have to include every edge this time. The requirement now is that we hit every single vertex exactly one time. So we've already seen that this graph is Eulerian. We can hit every single edge. Does it also contain a Hamiltonian cycle? And the answer is yes. If I start at this vertex here, I can go around the sort of L-shaped structure there. I've hit every single vertex one time. I came back to the starting point, and I didn't use all of the edges, but I hit all of the vertices. This graph, we can't do that with. And it's because of these three little triangles that are sitting on the end. If I start in one of the triangles, I could do that. I could start here and come out to this triangle here. But then what happens is I have to then, if I started on one of the triangles, then I have to go inwards to get to another triangle, and now I don't have a way back out. Because I'm not allowed to repeat vertices. I have to hit every vertex only once. So if I start on a triangle, then I have to go into a second triangle, and then when I go into that triangle, I don't have a way back out. But it's worse if I don't start on one of these outside triangles. If I start in the middle, then I still have to go out to these triangles, but now I have to go out to all three of them, and once I go into one of them, I hit a dead end. So this graph does not contain a Hamiltonian path, because at some point I'm going to have to go out to get to this triangle, and then I can't go back in along that same edge, because I'm not allowed to repeat these vertices once I've hit them. So this graph does contain a Hamiltonian cycle. In fact, it's a cycle. We come back and return back to our starting vertex. This graph does not contain a Hamilton path. Hamilton paths were first examined in the 1850s as an alternative to the question that Euler studied. Euler was interested in traversing edges in a graph and being able to hit all of the different graphs. But Hamilton was thinking, if we thought about the graph representing important cities or sites or landmarks in a foreign country, you might want to visit all of those major landmarks, all of those cities, but it's not necessarily important to travel every single road that connects the cities. If you think that the cities themselves are more interesting than the roads, this is kind of a natural question to ask. Is it possible to visit all of the cities exactly once? And it turns out to be a very hard question. Over 150 years later, nobody has figured out an if and only if condition that connects having a Hamilton path to other properties. So for Eulerian, we could say, yes, a graph is Eulerian if it has only vertices of even degree, and it's connected. That's it. We have an if and only if proof. If the graph meets these conditions, then it's guaranteed to be Eulerian. To this day, we don't have that for Hamilton paths. We have some close calls. We have some one-way theorems. And here's an example of a one-way theorem. So let's let G be a simple graph so that's no loops. And actually, I also need to make this connected. A simple and connected graph with at least 3 vertices. If the degree of x plus the degree of y is greater than n for all pairs of non-adjacent vertices x and y, then G contains a Hamilton cycle. And so we have this condition about the degrees, and if we meet this condition, then the graph contains a Hamilton cycle. But it's not an if and only if statement. If this condition fails, we still might contain a Hamilton cycle, but it's not guaranteed anymore. But it's a complicated definition. We have to look for all of the non-adjacent pair of vertices in the graph, check for the total of those 2 vertices of degree, and then we have to do this for all pairs. Okay? That's what the theorem says. I don't know why I put it on this slide and again on this slide, but I put it on here twice because it was that good. Let's talk about why this works for a moment. So we're going to prove it by contrapositive. We're going to assume that G does not contain a Hamiltonian cycle, and then we're going to find a pair of vertices that violates this inequality. Okay? So we're going to assume that G does not contain a Hamilton cycle. We're going to add edges to G until we can't add any more edges without finishing off a cycle. Okay? Let me explain what's going on here. So as an example, if my graph G was, say, had these 4 vertices in them. Now remember, Hamilton cycle has to contain all of the vertices and come back to its starting point. So it's clear that I can get to all 4 vertices, but I can't get back to my starting point. But I could add some extra edges. For example, I could add an edge from A to C, and that would allow me to have a cycle from A to B to C, but it wouldn't allow me to get to D. There's still no way to create a cycle that goes through all 4 vertices and get to the starting point. I could also add the edge from, I have to be careful. If I add the edge from B to D, then I can go, let's see, B, A, C, D, and then back to B, and then that would be a Hamilton cycle. not going from A to D, but going from B around to B. So I can't add this edge because that would create a Hamiltonian cycle. Can I add? No, that would be it. But I could add an edge and still not have a Hamiltonian cycle. So that's what we're asking to do here. Assume that G does not contain a Hamiltonian cycle. We're going to add edges to try to sort of fill up the graph as much as we can until any more edges would form a Hamiltonian cycle. And we're going to call that enlarged graph H. Okay. All right. So now we have this enlarged graph H. Let X and Y be two non-adjacent vertices in H. So in this case, this would be my X and this would be my Y. So they're not adjacent to each other. I don't have an edge between them. We have to have such a pair. If every pair of vertices is adjacent, then we have K sub n. That's the complete graph. We've seen that notation before. And K sub n always contains a Hamiltonian cycle on the outside. In fact, it also contains the diagonals as well. Like this is K5, but the cycle along the outside hits every vertex exactly once. So K sub n always contains a Hamiltonian cycle, and since H is not K sub n, at least one of these edges has to be missing, and now we have a pair of vertices that's not adjacent to each other. So we're guaranteed that we have these non-adjacent vertices. Okay, so by the construction, if we added xy to H, we would have a Hamiltonian cycle, because the rule is if we add any more edges to H, we would have a Hamiltonian cycle, and xy is an edge that we have not added yet. So that means that if adding xy would create a Hamiltonian cycle, then without xy, there is a Hamiltonian path. We get through all the vertices, we just can't get back to x. Okay, so it's missing the last edge to cycle back to the starting point. So label the vertices on this path, v1 up through vn, where x is v1 and y is vn. So here's x, here's y. This is my first vertex. This is my last vertex. And along this path, and I'm just going to straighten it out. We have this path from v1 through vn. Every single vertex is along this path. There are n vertices, and then there are n minus 1 edges. Okay. All right. So what we're going to do next, I'm going to skip this and come back to it in a moment. We've got this, all of the vertices are linked together. We have a path that goes through all the vertices. We're just missing the edge that would complete the cycle here. We don't complete the cycle. What we're going to look at is we're going to go through for every edge in this graph. So for every edge in this path, I'm sorry. So between VI and VI plus 1, we're going to look at the two edges that would connect the second vertex back to the beginning or the first vertex back to the end. Okay? We're claiming that one of these edges has to be missing. So H cannot contain both of these edges. And here's why. If it contained both of these edges, we would have a Hamiltonian cycle. And the cycle would go from V1 up through the first vertex, then around to Y, then back over through this path to second vertex, and then back to A1, V1. That would be a complete Hamiltonian cycle. And we're told that H does not have a Hamiltonian cycle. So let me back up now to the text here. So what we're looking at is we're considering this pair of edges from x to vi plus 1 and from vi over to y. Those were those red and blue edges that we drew over here. These edges cannot both be present, otherwise we would have a Hamiltonian cycle. We start at x, go up to vi, then we skip around to y, and then back up to vi plus 1, and then take this edge back to x. So that's important. What that means is that if I count up all of these degrees, well, not all of these degrees. How do we want to do this? This degree and this degree, the maximum degree of x would be n minus 1. If we, they're in vertices, if x connected to every other possible vertex, that would be n minus 1. And the maximum degree y is n minus 1. And so the max of the degree x plus the degree of y is n minus 1 plus n minus 1. But what we're told is that x and y don't connect to each other. And so that's going to take one vertex off of here. It's also going to take one vertex off of here. That is, the edge from x to y is missing. And that for every of these other, for every edge along this path, and there are n minus 1 edges along this path, one of these two edges, either the edge to x or the edge to y, is missing. And so there will be, in addition to these two missing degrees, there will be n minus 1 other ones. Either the red ones or the blue ones are missing in each pair. And so this is also going to be minus another n minus 1 vertices or edges from these different pairs. And as a result, the max degree is n plus 1, n minus 1 plus n minus 1 minus n minus 1 is just n minus 1. And therefore, since that's the maximum, the degree of x plus the degree of y is less than or equal to n minus 1. And that contradicts that it's greater than or equal to n. So that's the idea, is that we're showing that if I look at all of the possible edges out of x and y, there are n minus 1 pairs of edges where at least one of those edges have to be missing. And so the total degree has to be reduced by n minus 1. And that's what gets us the inequality there. So this is, like I said, this is as good as we can get for Hamiltonian cycles. We don't have a way of proving for sure whether a graph contains a Hamiltonian cycle other than to brute force through all of the different possible ways of connecting the vertices together and seeing if one of them works. But this is a theorem that at least guarantees that we have one in certain cases. All right. So that's it for today. Y'all take care. I'll see you again on Friday.